Hi, everybody. Welcome back to Dave's Math Channel. This is my feature on daily math problems, which I post on the Facebook group Classical Mathematics every few days. And this is the one I posted a few days ago involving a periodic continued fraction. Anyway, let's just begin. But the periodic continued, here's the problem statement. I'm asking for the continued fraction of this number 5 plus square root of 6 all over 7. I'm asking you to show your work. So that's what I showed on the previous slide. And there's a general method for solving continued fractions of this form. This type of number is what's called a quadratic irrational number. And in general, quadratic irrational number is a number of a form r plus square root of d all over s, where r, d, and s are integers, where d and s are positive, and d is not a perfect square. Um, so any number of that form is a quadratic irrational. It turns out that every quadratic irrational number has a continued fraction that's ultimately periodic. It might not start repeating right away, but eventually it does. Um, and there's a method for solving all continued fractions of this form. So first, I guess I have to tell you what the method is. Here's what we do. So you start with like I said, a general quadratic irrational number, the form x equals r plus square root of d over s, and I'm calling it x0 or x naught, if you like. That's going to be our initial value of x. This is an iterative procedure. Computing continued fractions is a recursive procedure, and this is just the first step in the recursion. So then what we have to do when we're doing any continued fraction, the first thing we do is we compute the leading coefficient, which is a0, and that's just the floor of x0. It's the floor of the number we started with. In general, a k is a floor of xk, but here we're just starting with k equals 0. So we calculate the floor, a0. You can always do that. And then once you have the floor, you have to calculate the remainder, and then you have to take the reciprocal of the remainder. And we call that x1. So x1 is 1 over x naught minus a naught. And if we plug in what x naught is, r plus square root of d over s, we're subtracting a naught from n and taking the reciprocal. And we have to do some simplification here. But when you're done, you're going to get this kind of ugly expression, s times the r prime plus square root of d in the numerator, and d minus r prime quantity squared, where I prime is a naught s minus r. You could just do the algebra yourself and check that this is the case. But anyway, that's what you get. And so yeah. So now we have to notice something that we would be fine if we so now we get x1, we can write x1 in a form that looks like x0. We have r prime plus square root of d over s prime, where I'm just simplifying the previous equation. S prime is now d minus r prime squared over s. If this is an integer, we're fine, but in general, it's not. It's going to be a fraction whose reduced form is a over b, where b is the denominator. B is in general not equal to 1. And if it's not equal to 1, then we have to kind of reinitialize things. We have to set some new parameters. R naught is b times r. Basically, we're multiplying r and s by b. So we say R naught is b times r, S naught is b times s, and now I'm defining this new thing inside the square root capital D, which is b squared times little d. And so now our initial problem is we're computing the continued fraction of r0 plus square root of capital D over s0. And now we can now we're in good shape because now we can apply a recursive procedure here to compute the continued fraction coefficients a sub k. Also, we can update our r's and our s, r sub k plus 1. So we have s sub k is r sub k plus square root of capital D over s sub k. That's just how we're defining the next real number that we're continuing the continued fraction coefficient of. And so the a sub k is just the floor of that thing. And then it turns out that r sub k plus 1 is going to be a sub k s sub k minus r sub k. And s sub k plus 1 is capital D minus r sub k plus 1 quantity squared over s sub k. That's always an integer, it turns out. So we just keep applying these equations recursively until we're done. Eventually, we're going to get to the point where we're going to get, r sub, we're going to get a repetition. We're going to get a value k such that r sub m plus p plus 1 comma s sub m plus p plus 1 is the same as r sub m plus 1 comma s sub m plus 1. And that's when we know that our continued fraction has started repeating once that happens. And so the pre-period is going to be m, the way I define things, and the period is going to be p. So anyway, it's probably better to see this in action. So now let's apply this iterative procedure for the problem that we started with, namely computing the continued fraction of 5 plus square root of 6 all over 7. Well, the first thing we do is we calculate the 4, and it's easy enough to compute the 4, 5 plus square root of 6 over 7. You don't even really need a calculator or a computer for this. You can just note that square root of 6 is a little bit bigger than 2. So you're going to have something in the numerator is a little bit bigger than 7. And the denominator is 7, so the result's 1. And that means that r prime is a naught s minus r. And if you calculate that, you get 2. 7 minus 5 is 2. And then s prime is going to d minus r prime quantity squared over s. That turns out to be 2/7. So it's not an integer. Our denominator is 7. And that means we have to multiply everything by 7. We have to multiply r naught by 7 and s naught by 7. So you get r naught equals 7 times 5 or 35. S naught is 7 times 7 or 49. And capital D is now going to be b squared times little d. B squared, b was 7. So we're going to get 7 squared times 6, which is 294. So those are the starting values we're using. And now that we have the starting values, we can go ahead and plug in the recursive formulas I wrote down earlier. And if you do that, you get this table of values. I'm not going to go through all the work here, but you actually computed these by hand. You don't really need to use a computer to compute these. You can just use the iterative formulas I showed you earlier for updating all these quantities, ak, rk, sk, and x sub k. And I think you can see from this table that we get repetition. X sub 12 is the same as x sub 2. In other words, r sub 12 is r sub 2 and s sub 12 is s sub 2. And that means that the pre-period was 1 and the period was 10. And you just go through the coefficients that we calculate. We already calculated the a sub k. These are the continued fraction coefficients. You just write them down in sequence 115. And then you notice that it starts repeating it repeats from a sub 2 to a sub 11. And the coefficients that are repeated are just the ones I show here in parentheses. 1, 1, 2, 1, 10. 1, 2, 1, 1, 16. So that is the answer. That's the continued fraction of 5 plus square root of 6 all over 7. So that's how you do that. Anyway, that completes my video for today. My light daily math problem. Thank you for watching. Long live math. And I'll see you guys next time. Bye.